All right, students, we're going to talk about coupled differential equations. And several parts of this assignment I'm going to not talk about, and I'm going to let you watch the YouTube video for IB vodcasting. Um, it's made by this man, Pablo Sanchez, and he just explains it amazingly well. So, anyways, he explains this part too, but I just want to quickly go over this part here, and I'm just going to show my key and talk this through. So, when Pablo talks about this, he says, look here, we've got the situation, and we've got these scientists. I'll let you read this. Um, but we're going to talk about an example. Suppose we've got a population of orcas and we have a population of seals. These populations interact with each other so that the change of the population affects both species. We therefore have two differential equations that deal with their population. So this dy dx deals with the population of the seals. And the changing, right? And this deals with the changing population of the orcas. Okay. So, what are the constraints for the variables x and y? Well, duh, they all have to be positive, right? I can't have a negative population of an animal. That makes no sense. So all the values have to be positive. Okay, question B. Suppose there are no predators. That means there are no orcas. Okay, so if there are no orcas, then that means the change of the population of orcas. So if y equals 0, then I can plug in 0 here and 0 here. And so using this equation here, if I plug in 0 there and 0 there, we end up with 0. That means there will be no change. Because the population can't grow if there aren't any orcas in the first place, right? You can't have more orcas if you didn't have any to begin with, right? So find dx dt and explain what happens to the population. So dx dt is this right here, 30x minus xy. So if I plug in 0 in for y, we end up with 30x minus x times 0, which simplifies to 30x. So the seal population is just going to keep growing. Okay, because there's no orcas to eat up those yummy seals. Yum, yum, yum. Eat them up. Oh, no orcas to eat them up. Okay. Suppose there is no prey. Suppose there are no seals. Okay. So if there's no seals, then the change, so if I look at the change of the seals, so if I look at this formula here, if x is 0, then I'm going to have 30 times 0 minus 0 times y. I'm going to end up with 0. So the population of the seals is 0, so the seal population is going to stay 0. Find dy dt, explain what this happens to the orcas. So the here's the orcas changing population. If I plug in 0 in for x, I end up with simplified to negative 30y. Basically, the orcas population is going to die because they don't have any food. Or they're not going to die, they're just going to continue going down until there's no more orcas. Okay, they need to eat something. Okay, so if x is 0 and y is 0 simultaneously, the population of both of them is extinct, and the change of both of them is 0. That should make sense. Hit pause to think about that if you need to. Okay, can we find another pair of values that are going to make them equal to 0? And the answer is yes. There is a way to find them equal to 0, and that's what our focus on this section is about. So this change and this change is going to be 0 when the population rates reach equilibrium. And we're going to talk about how to get to that equilibrium point today. Okay, question E. How can we find the solutions of these differential equations, which will tell us what happens to the population? So we need to solve both differential equations at the same time, simultaneously. And that's what we're going to be focusing on. So when they're being solved simultaneously, we're going to learn a little bit of vocabulary too. When they're being solved simultaneously, it's said that they're to be coupled. So that's why we've got coupled differential equations. We've got two derivatives that are affecting each other. And one of the things you're going to see a lot in this section, you're going to see an x with a dot and a y with a dot. And whenever you see the x with a dot, that simply means dy dt. And if you see the y with a dot, that simply means dy d. Did I say that right? This is dx dt, this is dy dt. Okay. Okay, so equilibrium points. So when the derivatives, when they're all equal to each other, that is called an equilibrium point. And we're going to talk about 6 kinds of equilibrium points. But for this first assignment, we're going to focus on stable fixed, saddle point fixed, and unstable fixed. The spiral ones we're going to talk about more in the section after this, which deals with complex eigenvectors, or using imaginary numbers with our eigenvectors and our eigenvalues. So stable is when as you can see in the picture, when everything goes to one point. Saddle point, we're going to talk about all these in just a minute, okay? But if these equilibrium points we're going to draw them using a phase portrait. And I'll be talking about what a phase portrait looks like in just a second. But the phase portrait basically tells us if we start off at a point, where is the change going to drive us and move towards? Okay. If we start off at a stable point, where is it going to take us to? Okay. Okay. So I'm going to talk through some of this. So for a coupled system of differential equations that are defined by x and by y, and they're independent of time. We're doing dt, right? So for any point x and y, therefore we can calculate a trajectory. That means we're going to start at one point, and then we're going to go in some direction. And we're going to talk about what direction it goes. And the phase portrait is going to have it's going to tell us where to go. So on our pictures, which you'll see on the next page, its trajectory is going to start at a point on the grid, and it's really similar to a slope field. From the last chapter, I guess it was. The difference is the vectors at each point on the slope field, there's a vector rather than just a line. And so each vector is going to have magnitude and direction, and so that's going to help us create our phase portrait. And you'll see what I'm talking about in just a second. Okay, and like I said, the trajectory starts off at a point, and you're going to get to see a solution curve, something like that. Okay. So, all right. Okay, so let's look at this first example here. Okay, so the phase portrait for a couple system is this, um, and so right now I'm not going to talk about how to draw the phase portrait, but I'm just going to show you if you're given a phase portrait, what we're going to do. Okay, in this chapter we'll show you how to draw the phase portrait in just a minute. So, but right now we're going to talk about the trajectory starting from the point 0 or 2 comma 1. So the first thing we do when we're doing a trajectory, when we've got a trajectory, we start at a point 2 comma 1. Okay, so when we're dealing with trajectories, we look at the arrows. And if you can see closely, the arrows, they look like they're going this direction, and then you just follow the arrows, and you can see that the arrows continue to go that way. When we draw our trajectories, and if we know we're going this way, we're going to be putting little arrowheads like this. This helps me notice what direction am I going. Okay. Let's do the next one. Okay, we've got a phase portrait right here, and we've got the derivative here. So right now, for the time being, don't worry about this right now. This created this graph. We're going to talk about how to draw the graph a little later. So right now, we want to calculate what's the direction from this point going to be. So if I plugged in 1 in for here, then we would have, so for question I, if I plugged in 1, I'm just going to call this x dot and y dot, because let's get used to doing that. So if I plug in 1 in for x dot and negative 1 in for y dot, so I'm going to plug in negative 1 minus 1/2 times 1. And for y dot, the derivative of dy dt, I've got sine pi and x is 1. Okay, so if I simplify that, I get negative 1 minus 1/2. That's going to give me negative 3/2, and sine of pi, it gives me 0. Okay. Okay. So, and this is the direction from this point at 1, negative 1. This is the direction it's going. It's going in x in the negative direction, and the y direction, it's not going up and down at all. Okay, for II, okay, so if x is 1/2, then and y is 1, I'm going to get 1 minus 1/2 sine pi over 2. Okay, so if x is 1/2, I'm replacing x with 1/2, and y is 1. I'm going to replace y with 1. Okay, and so this is going to give me a vector that goes 3/4 and 1. So at this point, 1/2, 1 up here, this tells me I'm going to be going up this direction. Okay. So, anyways, this tells us what direction we're going. We could make a phase chart like this, but we're not going to do that. So, illustrate on the curve with following initial points uh, for the phase portrait. So, I'm going to draw the trajectory starting at 2, 0. So 2, 0 starts right there. And I'm going to follow the arrows. So you can see the arrows. They look like they're kind of going this way and this way. Oh, it's going into a circle like this. Okay, so following the arrows, and you know it's close enough, right? If it's spiraling like that, it's hard to be pretty accurate. So this is going to deal with complex imaginary eigenvalues, but we're not going to focus that on this lesson. Right now we're just following how to draw trajectories with our phase portrait picture. Okay, so negative 1.5, comma 1/2. So negative 1.5, comma 1/2. That starts about right there, I think. Okay, and if I follow this, it looks like it's kind of going around like that. Okay. And ending up somewhere in here. Don't forget to draw those little arrows. That kind of helps you see. And this one was going this way, right? Those arrows really help me figure out where am I going and where did I come from. Okay, let's do our last trajectory. We start at 2, negative 1.5. 2, negative 1.5 starts about right there. And I'm going to follow this. And then it's going to go in here. Okay. Okay, so right now we're just following the arrows. And if it's close, then you've got the idea. Okay. Okay. Okay, so I'm just going to kind of walk through this one here. So I've already done this. So if I plug in 1 in for x, I'm going to have 1. And if I plug in 0 in for y, I'm going to have that, which simplifies to anything to the 0 is 1, and anything, and that gives us 1. So the vector that starts at this dot is going to go in that direction. And same thing with here. Now let's draw these trajectories. This one here, negative 2, 1.5, starts right here. Negative 2, 1.5. And then you kind of follow the arrows. This one starts at negative 2, negative 1. It goes like that. This starts at negative 2, 1/2. Kind of does that. Okay. Let's look at the next one here. Okay, so describe the equilibrium point. I know we haven't talked about this, but if I start at 0, 1/2, notice how it's symmetrical. It's not spiraling like crazy like the other one. So this is called the center point, and it makes a circle. Okay. Over here, 0, 1.5, this is called the saddle point, because above it, it kind of goes like this, and below it, it kind of does this sort of thing. So Okay, and we'll talk more about those things in a minute. Okay, but I've got my trajectory points and the directions. Okay, and okay, actually I'll just show these here. So for each of the following portraits, locate and describe the equilibrium point. So the equilibrium point is where it's kind of doesn't seem to be changing, and so we've got an equilibrium point, and if I look at the examples, it kind of looks like it's going out and spiraling out, right? So that's called an unstable spiral, and these names and definitions are on this page right here. Okay. And here I've got an equilibrium point, and here we've got a saddle point. Kind of if you pick some different trajectories, you'll see that it kind of goes this way and then it kind of goes away. Okay. We're going to focus on this one today, this type of drawing. Okay. An unstable fixed point. It's like we start at a point and everything is going away and from that point. And a center is when it just goes around in a circle. Okay. And lastly, here's a phase portrait with a spiral. And just if you picked any point, it just seems to go in like that. And okay. Okay, so the next few pages, I'm going to have you follow the instructions that you'll see in your packet. So I'm going to need you to follow the instructions from this website. If you go to YouTube, and you type IB, any of this, any parts of this, you could just type in this part right here, and you'll get a video that explains in detail on what to do here. Okay? And then when you get to this part right here, there's another video, somebody explaining what to do here. He explains it so well. If you need help on class, I can help you with that. And then same thing here is part 4. He explains the 3 different eigenvalue real phase portraits. So he explains how to draw the phase portraits, and this is a very, very good one, especially the saddle point example. Then he does an example here with an unstable fixed point, and then finally he does one with a stable fixed point. And in my next video, my part 2 video, I'm going to explain how to do exercise 12F, the 3 examples that I have on the packet.